side of this, we are going to say it is an eyeball. How do I draw an eyeball? Is that grotesque? Is that grotesque enough?
No, it's working. It's working.
All right. Well, we're online right now. It's Beanie Town. Beanie Town, USA.
Beanie Town. What do they call Chicago? Beantown?
Boston is Beantown.
Boston is Beantown. Okay.
Chicago is the Windy City. I'm sure Chicago is also some form of town.
It's just Chi-Town. Yeah.
Chi-Town. Chi-Town. There you go. Yeah.
Yeah. Why Beantown? Why do they call it Beantown?
Boston baked beans?
Is that it? All right. I mean, it's tasty,
I don't know how prominent of a dish that actually is in the city of Boston or in the state of Massachusetts, but maybe it's one of those things where people outside of this call it that. That's all they can think.
Right. Inside the city, they just call them baked beans. They don't need to put Boston in front of it because they're in Boston.
Well, it feels like a dead giveaway when somebody refers to San Francisco as San Fran, right?
Ooh, or Frisco.
Yeah, I don't know if anybody even says Frisco, but San Fran is pretty close to that.
I've definitely had like friends from other places be like, "Oh, are you still in Frisco?" And I'm like, "Am I?" I don't know.
Yeah, Frisco is like literally you're like going out to Frisco with my pickaxe and gonna pan for my fortune, right?
And you know what? That is kind of how I ended up out here. So yes.
It's true. Yeah, you walked into the bar, someone was playing like the Maple Leaf Rag on the player piano, and like you asked for bourbon at the wood.
It'd be a much cooler city if someone was playing Maple Leaf Rag on pianos in all the bars.
Yes.
That's like a solid improvement. 10 out of 10.
Yeah. Yeah.
Not so fortunate.
Yeah, Bunny and I have been watching and rewatching the show Midnight Diner. Do you know this show on Netflix?
Midnight Gospel?
It's called Midnight Diner. I think it's
Midnight
probably
Diner?
Different.
No.
It is. It's just like a slice of life show about this guy who runs this tiny bar. Did you ever go to Golden Guy in Tokyo?
I did. I went to Golden Guy. Golden Guy is truly a strange experience.
Yes, it's really strange. I've only walked through Golden Guy. I haven't actually eaten any of the places, but he has basically one of those eateries at Golden Guy, and like every episode is like a little vignette about one of his customers, basically.
Oh, that's cool.
But the delightful thing about that show is that like everybody's like friends with each other at that, and it's like kind of like this place of no judgment there. He's kind of like the bartender that listens to you talk about your life kind of thing.
I love it.
But so I was thinking that like I needed a watering hole in Berkeley that was like that, even though I don't really drink alcohol. So I'm not sure what that's going to be.
Yeah. Oh man. The XOXO folks in Portland opened a zero proof bar. That was like, it was like bar culture, but like they only make non-alcoholic cocktails, which is
okay.
What I want. It's perfect.
So it's like 100% kombucha there because it's Portland.
No, it was like cocktails.
Nice.
Yeah. Portland zero bar. They were sending Sucker Punch. There you go. They were doing home zero proof cocktail kits for the pandemic.
That is awesome. I will patronize them because
it's as available as a PS5.
Damn it.
Yeah.
Can they at least bait and switch me or like put me in a queue?
Were you in a queue today?
I want to like add it to a shopping cart and then not be able to buy it. You got as far as like actually paying for something, right?
Yeah, I paid for it once and then I got my money back.
Well, that was Kohl's, right?
It was Kohl's, which like I don't even know what Kohl's is. It turns out they gave me like $200 of store credit for that. That was like the bonus for buying it from them.
Yeah.
And they gave me back my money, but they didn't take back the store credit. And they were like, yeah, sorry, like that's yours now. Enjoy. So I bought like a nice picture frame for my grandma.
Did it cost you $200 in Kohl's credit?
It did. It's a digital picture frame.
One of those, yes. Yeah.
Yeah, that like I put her Wi-Fi info in, and I can send pictures too of her and like the great grandbabies and stuff.
That's
And
brilliant.
like, yeah, and hopefully no configuration, and it just works for her, or it's a disaster and she can throw it in the trash. But it was free.
Yeah. Well, I'm glad that you got that out of that experience.
Yeah.
And you don't
Jeff,
really need a PS5, right?
did
What
did
the
you
fuck
see
is this?
did you see the Philly series? uh, it's a cheesecake.
Wait, what? Oh, so the thing on the top is like a. Oh, what? Wow, they had to like. They probably spent like at least $1 million on this, right? They had to build the
I
website and they had to
I
like
assume
market.
you're
Yeah.
right. Yeah.
Amazing.
Yeah.
I'm
It's
glad they
great, and
did
also,
this. Yeah.
well, even better, it's also out of stock. Oh shit, there's a queue. All right.
Oh
I,
man.
what, that wasn't there the last time I came here.
Wait,
I
could
might
you
have to buy
actually
it.
buy it? Do you have people eating it? Or is this just a joke? Is this just like a very elaborate joke?
Uh that's a great question.
I don't think anybody's actually eating this.
Maybe they put it up, said it was sold out, and then they're like, oh shit, people wanted it. Come back in 5 days.
Yeah, unless there's like an actual unboxing on YouTube, it didn't happen, right?
Yeah, that's a truly excellent point. Unboxing. Nope.
Yeah, no, it's not real.
Yeah,
Yeah,
I don't
100%
believe it.
fake. Yeah,
Yeah,
it's
totally.
fake. Kind of makes me want to buy cream cheese though. So mission accomplished. Just
It
fly
worked.
that banner on the aircraft carrier, baby. That's. I wonder how many people, if I tell that joke to them, like won't get it at all at this point.
Wasn't that like the year 2002?
It was the year we invaded Iraq, so I want to say that was
Yeah.
2003. Yeah,
Boy.
I've been making that reference like at least 2 or 3 times a year up until like 2020, and just now am I realizing that like nobody gets it.
All right, there's about to be 18-year-olds who weren't even born when that happened.
Yeah, people of voting age, incredible.
Yeah. Who won't understand. So that's a bummer.
Yeah. Whatever, the way things are going, each generation is going to be, more impoverished and more under the thrall of the previous generation. So we own them basically. Anyone who's 18 right now, we essentially.
I see. So you're taking the extended boomer strategy. You're like, you know what? Boomers got to do it. I need to roll some young people
paying
too.
it forward is what I'm doing.
Yeah, it's the if I paid off my student debts, why should they get free college?
Yes, I paid mine off. Do unto others what was done to you.
Has some super solid reverse socialism there. I like it.
Yeah. I believe it is a philosophy about of society based purely on the concept of vengeance, which I believe anybody can agree is like a pretty solid way to go about things.
Oh lordy! All right, I'm seeing some drawn over here.
No, I just wanted to make sure it worked.
Works.
Hello world. We're using the software called Miro here. It's free. We're probably never going to pay for it, but it's pretty good.
It's pretty good. Yeah.
Trying to figure out what the adequate zoom level I should be using here, so that like I'm not drawing things too small. So I'll try to match the view that I'm seeing in OBS here. And I think I've approximated. You're at 39.
Nice thing is I can zoom and pan and do whatever you need to. So
okay. All right. Well, I'm roughly approximating what I'm seeing here, and I'm going to erase my greeting here because I don't actually mean it. I don't want to say hello to the world at all. I want to just stay in my house until the
it's the most
pandemic
antisocial Twitch stream ever.
Yeah. And then when the pandemic is over, I'm going to continue to stay in my house and work on this video game.
We are about to be in shelter in place again, and I am super sad about it.
Oh, yeah. They're gonna not even close down outdoor dining, right?
Yeah, I mean, I think they laid out the rules, which is like as soon as your ICUs fill up, uh, you're screwed. Which seems like far too little, too late. But I guess we're gonna do it.
Is that going to happen in Alameda County?
They laid out rules for the entire state. They're like when you hit X capacity, the entire thing shuts down.
Damn.
And we're lumped in with Bay Area and San Francisco, uh, and like South Oakland. Like we're a bigger blob than just counties now.
Yeah. God damn. We really
I bet it'll be
we
next week.
really screwed the pooch on this pandemic thing, didn't we?
Yeah. Who could have predicted this? Just about everyone.
Yeah. I think
somehow it's
I think
still
we
a
actually
worse-
did predict this, did we not?
It's still a much worse pooch screwing than even I imagined.
Yeah.
My imagination was not vivid enough, is what happened.
God.
Yep. It's okay. It's more time to make video games.
Yeah, let's do it. What are we talking about today?
I think we're talking about perspective.
Okay.
Because we've got this beautiful green tile,
Yeah, I love it.
but it's not doing a lot for us right now.
It's pretty hot. That's a hot green tile. Is that solid green? Is that 0.010? Is that our color?
Oh yeah.
Yeah.
You know it.
Oh, we have a cute little table there too. I like it.
Yeah, are we using this? I think we're using this. Yeah, we totally are.
Dude. Look at that brilliant factoring of this. This is the most well factored magenta, like green on magenta program there is. Let's talk about perspective, right?
Yeah. Back to the Miro.
How much do you remember of perspective from your graphics class?
Extremely little. It's a matrix multiplication.
Yeah.
Yeah.
Okay.
And for some reason it's 40.
Mm-hmm.
Is that correct? Yeah.
That is all correct. If we get to matrices today, I won't call that a stretch goal, but the important things come before the matrices, I think. All right. So perspective. How do we draw a scene in perspective? Here's a horizon. Here's the sun. Boy, it's a gorgeous scene. And imagine a really long cabin or building of some sort. And basically the way that you would draw this, and let's say the cabin is like of a consistent height and width, but it kind of stretches towards the horizon. And I believe in 2D art, you have this notion of a vanishing point where all lines will go, right? Is that
Exactly.
correct?
Yep. Oh, so interesting. Your line shows up after you let go of the pencil. How fascinating.
Yeah, and then maybe you have little doors, right?
Mm-hmm.
And I'm trying to make sure that I draw the doors. Imagine the doors are supposed to be the same size. I'm not sure if I'm achieving the effect.
Roughly. That seems like a challenging thing to draw.
Thanks for
at this scale.
Yeah. It's challenging. But the reason why I'm screwing it up is that you need to kind of make them consistently. They need to get smaller and smaller as they get further and further away from the foreground as they move to the background, right? However, this is actually not a 3D drawing, right? It's not actually. You're not actually wearing VR goggles to look at this. This is actually just a 2D image. Ceci n'est pas une pipe. Yeah, this is actually just a two-dimensional thing that we're just looking at, and our brain knows how to basically read this as if it was a 3D scene. And the thing that gives us the hint that is 3D is that we have this thing called foreshortening, which is the idea that there are certain objects that we imagine being the same size, but if one of them is further away, it will actually appear to be smaller, right? And it would be literally drawn as, so if I had a square in the foreground or a cube in the foreground, and then I had the equivalent size cube but way in the background, I could just draw it really small, and that would basically simulate the illusion of it being further and further away, right? Yeah. So that's more or less what we're trying to achieve is foreshortening, but with our 3D graphics, right?
It's fascinating to me that we're just trying to like mimic some tricks our brain does for us to interpret the world, but we have to recreate them in a digital environment.
Yeah, and it's actually not just our brains. It almost maybe precedes the brain a little bit because I think what we're actually going to do is mimic what an eyeball does, or really what a camera does, actually, in a manner of speaking. So if I were to scroll down, I want to keep my drawing, but basically I've moved the foreshortening image off the screen. I'm trying to think about do I want to do an overhead view or a side view? I think overhead view, side view makes a little bit more sense. So can I draw lines with this? Is that possible?
Yeah, are they in the?
Yeah. Let me see what did this do.
Oops.
Do you see my line? You don't.
I do. It's a thin line.
It's very thin. Can I change the thickness?
Yeah.
All right, that might be too thick. Let's see. How do I adjust the thickness of this thing? Ah, here we go.
When I tap on it, yeah, in the type.
There's a little. Very cool. All right, I like the 3.1. Let us say that this is kind of like. Oh, I wish I had done the one with the arrow. Why am I? Can I add the arrow after the fact?
I was just like, can you change it? Yeah.
That would seem to be the advantage of doing this, using this kind of program. Oh yes, I can. Oh yes. Oh my god.
Neat.
This is the greatest thing ever. So on the left side of this, we are going to say it is an eyeball. How do I draw an eyeball? Is that grotesque? Is that grotesque enough?
No, it's working. It's working.
Okay. And the eyeball is going to have some, and so this is actually a side view of a person's head. So we're still in 2 dimensions, but we are using one of the dimensions is the z-axis, right? And in OpenGL, this is actually negative z, or z gets more and more negative as you move to the right or farther away from the eye, right? The eye is our focal point, right? You're going to have some kind of field. You're going to have some field of view that is symmetric around the eye. Let's see how amazing this is going to be. Oh yeah, I like this. And there's going to be something equivalent on the other side, and I'll roughly try to make sure that the angle is kind of the same. It's sort of the idea that I'm trying to get at there. Did I succeed? Does that look roughly like that? All right. So if you have an object that is sitting above, you can see my pointer here. Oh no, wait, that's dragging. Didn't mean to move that. Sorry.
I can see where your pointer's at though.
Still learning how to do all this stuff. Maybe I'll just actually mark it. So anything that's up here or down here, you're just not going to see. You'd imagine that like your field of view for like the vertical axis is pretty good with your eyes, but like you can probably raise your hand in front of your face up to the point where you can't see your hand anymore. And what that really is just saying is that like your hand is above this dotted line. But the further away something is, the higher it can be and still be in your field of view, right? The reason why that's the case is that we are imagining that essentially what your eye can see is anything where light can hit the eye, and the light is traveling in a straight line towards the eye, right? So we've got light rays kind of traveling this direction and this direction and this direction, all going into the eye, right? Okay, so that much I think is pretty straightforward. I think it conforms pretty naturally to our intuition of how this stuff works. Now to do graphics, um, we need a notion of a plane of projection. And when it's a camera or someone's actual eyeball, the plane of projection is actually over here. And what happens when you get a light ray? Let's say you have an object that's here, right? If we just draw a line that connects the object to the focal point, right? You're going to get a light ray that does this. And if it goes through the focal point, it'll hit the plane of projection underneath, almost like on the like below the focal point, right? So it's above the focal point, and when the actual physical object is above the focal point, out in the field of view, but the point at which it hits the plane of projection is below the focal point, and that's just because it's going through the focal
moves
point
in a straight line.
Yeah, it just moves in a straight line, right? So you've probably heard before that like your eyeball is actually like it does a mirror image and an upside down flip of what the real world is like, and then your brain has to compensate from that. The same thing actually happens with a camera, right? Dom, you're a photographer, right? So if
yeah, I can go grab one for you too if you want.
we can actually show it up. This is what a camera looks like. And what's the equivalent of the focal point on a camera? Is it the actual where the aperture actually is?
So yeah, the focal point, the center of the eyeball, or the dot around the eyeball here is like the center of the piece of glass, essentially.
Yeah.
After it's gone through however many prisms it has, and back here is the fill plane.
Yep, and that's where the film is, right? And indeed, the reason why the piece of film, when it's developed, is called a negative is because it's reversed and upside down, right? And then when you
actually no, it's because you actually get the invert. You get invert.
Oh, they use a mirror to invert it. In the camera itself.
No, it's that this is a different chunk of chemistry, but the silver. I mean, in black and white, it's silver. The silver emulsion sticks to the plate where light hits it and falls off where light doesn't.
Yeah.
So where light touches it becomes black, and where there is no light becomes clear or white. So you get, it's just actually a chemical reaction that we have a negative.
So, but the thing is, if you were to use a pinhole camera, right? I don't know if you ever made a pinhole camera with a shoebox.
Oh, yeah.
Like that. The actual.
I've made one in a tent. Yeah.
Yeah. The actual.
The image is not a negative, but the flip is upside down.
Yes, it's upside down.
Yeah.
Right.
Yeah.
Yeah. It's upside down and probably reversed left to right. And then when you develop that, you basically do that process in reverse, and you get it back to looking like the real world, right?
Exactly. Yeah.
Yeah.
I guess the thing about the film and the upside down is that, like, yeah, it's to fix it, you just turn it over, which is great.
Yeah, exactly.
But the actual process of being a negative is much more weird and complicated.
Okay. So for 3D graphics, we don't do anything fancier than this. The only thing that we do is we move the plane of projection in front of the eye, so we don't have to do any inversion. So let me draw what that looks like. Let me actually get rid of the eyeball. It's kind of messing me up and creeping me out.
You didn't like the eyeball?
Well, it wasn't actually at the intersection of all of those points there. So that was also.
That's a terrible camera.
Yeah. Oh yeah, that'll work there. So our plane of projection is actually going to be, let's just say arbitrarily right here. Gonna make it a little thicker.
By the way, I locked the back 3 lines, so they can't be moved anymore.
Oh man, can I lock the plane as well? How do I do that?
You can lock anything. You click it, and then there's a lock icon.
I don't see the lock icon. There we go. I locked it. Nice.
Yeah. Yes. Now no one can move around, which is really, really helpful.
Okay. So what's interesting is that, like, we're essentially going to get if we move the planar projection in front of the camera, in front of the focal point, we're actually going to get an image on the planar projection that is basically what you would get if you develop a piece of film. You'd get the right side up, non-flipped on the left and right image, and that is exactly what a 3D graphics simulation does. So what we would do is basically what the question you're ultimately trying to ask yourself is the object, the dot that let me actually draw two dots because I think that'll help illustrate. Say if I have a couple of dots. I didn't put enough separation between them. Okay, so I've got a couple of dots now. And the question is like, where on the plane of projection should I draw those dots, right?
Mm-hmm.
And then just for the sake of really beleaguering the point, let me draw another dot up here as well, right? So all we do is we attempt to draw lines from the object to the focal point, right?
Mm-hmm.
So let me go ahead and do that. Oops, didn't mean to do that. So getting used to it, but I feel like this is working pretty well, right?
This is nice, yeah. I especially like that we have shared edit access versus just a scratch pad.
You can kind of clean up my mess a little bit too. Oh yeah, change the colors. That's perfect. You got the mouse there. That's great.
Right, yeah, I got mouse control and pencil control. A little bit of everything.
Okay, so point number one doesn't intersect the planar projection at all. We're kind of going over what we were talking about before because it's outside the field of view, right?
Yep, correct.
And then point number two does hit the planar projection, and so does point number three. They're both within the field of view. But what is interesting about point number two and point number three is that they're actually closer together on the planar projection than they actually are in the physical world, right? And
So
that's just that's just the way that that's just the way that light works, right?
Mm-hmm.
And there are actually ways in which objects can obscure each other, right? I think this is probably fairly obvious, but like if I had point number 4 here, you can almost kind of imagine that it is completely obscured by point number 2, even though it's like actually in a quite different location than point number 2, right?
Yep, absolutely.
Yeah. All right. So this actually works on both the X and Y axis. So there's a way where you can look at this, and it's like it could be the side view of someone looking straight ahead. But imagine flipping it, rotating it 90 degrees, and this could be an overhead view as well, right?
Yep.
Imagine this
is
an
that makes
overhead
sense.
view, right? It works the same way on both axes. And the way that you actually, so the real question is, I know, let's say point number 2 has, let's say this is actually like the side view. So what you actually have for each of these points is its y coordinate, how high off the ground it is, or how above or below the plane of the the level of the eyeball point is, and you also know how far away from the eyeball it is, right? So for point number 2, we essentially have a y and z. Draw that a little bit more clearly. We have like y2, z2, and we also have y3, z3. These are our visible points, right?
Mm-hmm.
The question we want to ask is, what is this y value? And what is this y value here?
Gotcha.
Right.
Right, because I've seen this done. Like, I remember doing this exercise where I wrote a ray tracer essentially, where you actually shot a beam out
Yep.
and tried to touch something.
Yep.
And you rendered it that way, but it turns out that's not a very fast way to render something.
It turns out it's not very fast. Yeah. Now ray tracers actually have to do this because what they do is they project a beam from the eye. And in fact, if you want to do it really correctly, you project one beam for every pixel that's on
Exactly.
the plane of projection. And not only that, but you probably have to bounce it as well, right? Because you will also bounce it off of objects that the ray hits.
Yeah, that is the CS class algorithm exercise I remember doing.
Mm-hmm.
And it was cool, but it was definitely like kind of a brute force approach to 3D rendering, but also like a correct physical modeling of it. It's like pretend to be light, do it like light.
Right.
This is a very interesting way to do it.
Right. So let's call the distance above or below the like let's call on the plane of projection. I think maybe what we can call
Jeff, Kirky's little daughter's watching us stream and enjoying the plane of projection.
No way, that's awesome.
Yeah,
hey
this is really cute.
I'm glad you're online.
Hi, Rylan.
So why don't I call like basically our displacement between on the plane of projection, let's call that the S coordinate. It's like an S value, and it's like basically the screen value, like where on the screen are we drawing this object, right? Where, like, and so what we're trying to find out is the S value for object 2 and the S value for object 3. And that's where that's basically where their images intersect the plane of projection. Right? So what we're trying to find is S2 and S3. What are these things? And it turns out that the geometry of this isn't too bad. For me, this was 9th grade geometry, right? And we use a notion called similar triangles, right? Let me try and get a different color here. Let's just say we're looking at S2, there's a triangle here. And I want to use that color. This is good. And then there's a triangle here. Right? And what's the word for triangles that have the same angles, but they're similar, right? They're similar triangles. I think that's what it's called.
They're similar triangles, yeah.
Yes. They're similar triangles. They don't have the exact same measurements, but they're proportional to each other because all the angles are the same, right?
Oh, dude, that's why it's a multiplication.
Yes.
That's cool.
Yes.
That's really, really cool.
And then there's one value that we haven't talked about yet, which is this one.
Is it W?
And we call this one D. I don't know why they call it D, but this is basically what we call the focal length, right? Cameras have a focal length.
Mm-hmm.
This is actually what you move back and forth when you are, I believe, when you are attempting to focus a camera. Is that right?
Yeah. I'm gonna grab the giant camera out of my closet because it's just a fun thing.
Yeah.
What are these bad boys?
Yeah. Oh, whoa. What is that? Is that a medium format?
No, this is a 4x5.
Okay.
Turn off.
That's really cool. And so this one, you can actually do very complicated things like oblique projections and that sort of thing, which we won't talk about today.
Get that tilt shift going? Yeah.
Exactly. Yeah. Yeah. An oblique projection is when the plane of projection itself might actually be tilted, right? that's essentially what we would do. Is like right now our plane of projection is
I've got
kind of
controls
straight
for
up
that.
and down. Yep.
Showing this off, but you keep talking about this camera in particular.
Yeah, exactly. I'm gonna get rid of point. I'm gonna get rid of 0.3 because it's right now it's kind of cluttering my. It's kind of fighting me a little bit. So all we really care about is point number 2 for now. How's that sound?
Okay.
Now, what the law of similar triangles tells us in the language of analogies is that the screen position of point 2 is to the focal length as the y position, so the physical position in real space, is to the distance of point 2. We try to make my z's and 2's really, really different from each other, right?
Okay. Yeah.
So another way of expressing this is that the ratio of screen of point 2, the screen position of point 2 to its distance from the focal point, which is specifically the focal length, right, is equal to the physical position in world space of that of point 2 divided by its physical distance from the focal point, right? All right. So what that means is that we just do this. This is just our algebra. Right? And if we wanted to actually include both axes, both the x and y axis, what we'd say is that the y position of point 2 on the screen is the y world position times the focal length divided by the physical distance. And then the x position actually is going to look really similar. The only term that changes
is x,
right? So you are dividing, all you're basically doing is you're taking the y world position and dividing it by its distance from the focal point, and then scaling it out by whatever the focal length is. That's basically what the math is here. And it's no more complicated than that.
That is really clever
in terms of the basic concepts, right? So just similar. So if we scroll up to my drawing, I don't even know if my terrible foreshortening drawing. I don't know if
all the way up there.
I don't know if the math translates there, but the notion that everything is kind of like it's kind of squeezing together, it just means that the farther away it is, you're just that the thing the sort of the denominator of that division, which is your z point, it's just basically saying I'm going to bring you closer to the center as z gets higher and higher and higher, right? That's sort of our this is vanishing point math, basically. Yeah, and so this is how we get our foreshortening, right?
That's so neat. Okay.
Yeah. All right.
Wow. So this math actually makes sense to me. That's great.
Yeah. So I'm gonna bust out with my book. This is the book that I use. I don't know if the Zoom's gonna let me do it, but
I like that when you pull the book up, it's just like there's not even a human here.
Yeah,
Virtual
it's
background.
it's just the book. This is a well-loved book. I mentioned it last time. Essential Mathematics for Games and Interactive Applications. I would kind of recommend it. I think for folks that have gone through your engineering curriculum and maybe have at least some familiarity with matrix math, I think it's okay. But they're also really excited about describing certain transforms as affine versus some as linear. And for me personally, that doesn't really get me going. It doesn't hit me super hard, or at least not yet. So there are ways of learning this stuff that I think are a little bit more intuitive in the way they go about it. So the question is like, basically, like, how do you do this math quickly, right? I'm scrolling it down. If you scroll down over these formulas, the question is like, how do we do this stuff quickly? Because basically what we can do, this is a perspective transform. We basically can take the world positions of things. I remember in our OpenGL code, we were basically putting world positions into at least the beginning of the pipeline.
Mm-hmm.
We need to do something to those positions to adjust them, to squeeze them down, or to move them around, to put them in their right positions on the plane of projection, so that we can render them screen, and it's rendered in such a way that our eyeballs read that as saying like, okay, we're looking in 3D right now, right?
Mm-hmm.
Yeah. So what you could do if you're just doing this in software is you could literally just go over every single point, every vertex in your set of geometry, take the y value, divide it by z, and multiply it by the focal length, which is d, and you'd kind of be done at that point, right? So why don't we just do that? Like, why don't we just like make our hardware just do that and be done with it, right? Why do we need to get into matrices and that kind of thing? And the reason for that is that it turns out the nice thing about matrices is they can be composed, right? You can basically, like, if you have
you can cross product for days, basically.
You can cross product for days, or rather, you can matrix multiply for days, right? So there's a series of transformations that you do to take a world position, or really a model position, and transform it into a screen position. So your goal is to take a model position. That's basically where your stuff starts, and then take it all the way to a screen position. And there is a lot of stuff that goes on between this, right? Your model position is like what your artist is doing. They're like sculpting the T-pose. You know, you've probably seen like Blender or whatever, there's a T-pose, and like your nose is a certain distance from the origin. I don't know what the origin of models usually are. I think it's probably the point between the feet, but I could imagine that it could be the center of the T as well. I'm not actually sure. It's whatever
yeah,
whatever the convention
either
is.
way.
Yeah. So what you're trying to do is actually, let's say you got your guy who's like a T-pose, a stick figure, and you're trying to figure out where the top of his head is on the screen. So first of all, what you have when you're working with this geometry in code is you look at the model and you say, okay, the top of the head is like 1 unit above the origin. But that is relative to the center of the model. That is not relative to where the entire model is placed in the world, nor is it relative to where the camera is in the world, right? So what you actually have to do is you have to go through this series of transformations where you go from model to world to what is known as the view space, which is also the camera space. And then you take it to screen space. There is also there's also a detour here into what is known as clip space. And if we can get into talking about that, then that's a stretch goal right there. That will be an amazing goal. That would be an amazing success for us. Keep in mind now that we are already like bumping up against the very limits of my knowledge about this stuff. Like I can kind of talk about it in a hand-wavy way from first principle, but my like actual intuition about this is basically as shaky as it sounds as I'm communicating to you right now. So why matrices, right? Well, it turns out that each one of these arrows is a matrix multiplication. We can take the original model position and compose it with some world transform, and then compose that with some view transform, and then compose that with some perspective transform. I can't use the letter P again. So I think I'm gonna call the position D, and that just stands for displacement as a physics thing for you. And then you have your perspective transform, right? So what it turns out you can do with matrix multiplication is you're going to have to kind of repeat this operation for every single vertex in the model, right? But it turns out that for every single vertex in the model, the only thing that's changing is the d sub m there, the position relative to the origin of the model, right?
Mhm.
So wouldn't it be great if we didn't have to like remultiply the perspective transform times the view transform times the world transform?
Gotcha. So that's it. So we feed this into the. I mean, this is what was fed into the uniform for the OpenGL renderer.
That's exactly
Yeah.
right. So basically, what we
Cool.
were what you can do is just kind of like put this into what we'll call the composite transform. It is like the sort of like amalgamation of all those transforms, and then multiply that by the position. And you can do this for every vertex, and each vertex is going to have a different d sub m, right?
Yep.
And the fact that you've smashed those matrices together means you're not repeating work. This is a don't repeat yourself proposition, right?
Nice.
Yeah.
That's clever.
Yeah, it's pretty nice. It's a really, really nice system that miraculously works. It probably took someone to, like, all of this stuff is ultimately just arithmetic, right? Matrix multiplication is just an algorithm of multiplication and addition, really basic stuff. But some genius, probably Gauss or somebody like that, figured out that it has all these like properties where it's like, well, wait, I can pre-multiply all these things together, and it's like it has the same effect, but now I can do less work, right? So,
Yeah.
yes.
No, it's just wild.
Yeah. So there is a problem here. Matrix multiplication, as I said before, is the result of addition and multiplication. Nowhere in that is division, right? And that gets a little bit tricky, right? Like, how do we get this like the points that we in screen space are divided by the z coordinate, and you can't actually accomplish that using a series of matrix multiplications, right? So what that means is the perspective transform is not linear. Linear is the linear in linear algebra, right? It basically means you cannot express it as a series of matrix multiplications, right? And then that actually makes sense, right? If we go back up to the drawing, or even if we go back up to the kind of like side view camera thing, or actually, let's go to the drawing. Actually, I think the drawing makes it really, really clear. This is clearly not a linear transform because the way that I've drawn it makes parallel lines no longer parallel, right? Like in physical space, a lot of these lines are parallel, like the sort of edges of the top of the house here or the building.
Correct.
But
Yeah, they should never converge.
Yeah, in screen space, they do converge, right? They do become non-parallel, which means that they're going through some kind of non-linear transformation because like a linear transformation preserves parallel relationships between lines. It can skew things. It can basically make things that were once perpendicular with each other no longer perpendicular. That's allowed with linear transform. But you're not really allowed to violate parallel lines, right? Like lines that previously didn't intersect will now intersect on, theoretically in perspective transform. Right. So the way that this is actually kind of represented in a matrix form is that you figure out a way to kind of like do all of your perspective stuff, but also pack in some information where you remember what the z value is. You remember what like the world space z, or like the view space z rather, the distance from the camera. World space z and view space is different in that the camera itself is moving around the world. But what you actually want to do when you're rendering stuff is you almost want to move all the objects. You want to translate them and rotate them so that the camera acts as the origin, right? And that's actually not the way that you move stuff around when you're simulating them. When you're simulating them, you basically want there to be a fixed world position and let the camera float within that world position. Because otherwise, it'd be kind of too hard to kind of like say, well, I want the camera to follow this object. But if that object's position is relative to the camera, if the camera's always the origin, then it gets kind of gnarly. When Steve was on the stream a couple streams ago, do you remember how he talked about Outer Wilds?
Yeah, that was honestly mind blowing that the game moves around the player.
Yeah, I don't know. Did you? I don't know. I put in the notes a couple streams ago a link to the documentary that he mentioned, and they talked to the people who made the game, and they said that like unlike a lot of games, the player's position is the origin at all times, which is wild. So that's the exception.
So weird.
Right. The reason why it worked for Outer Wilds is that every object in that game is moving anyways. That's basically they justified it by saying like, you know what? Everything is moving anyways, right? Everything's like orbiting everything else. Everything's moving around anyways. It's not actually that much more expensive to us to apply a force to every single object in the game when the player moves. Basically an opposite force. So that so basically, the universe is moving towards the player, player rather than away from the player. Yeah, so
that's it, because everything is already being transformed every second. Oh wow, okay, yeah.
So it's a constant time cost and not more than that, because basically, like all you have to do is iterate over every object and add whatever the opposite of the force that you're applying to the player or something like that.
Yep.
Yeah. Or that you would apply to the player if the player was actually moving relative to the origin. That's a long digression. At any rate, what you're trying to achieve with your matrix multiplication is consuming model space coordinates, right? That's actually what we're actually, how we built up those vertex array objects last stream. We created all of that stuff, all those vertices. We're not pre-computing anything really. We're basically taking what the art program, Blender or whatever 3D Studio Max or Maya or whatever program we use to sculpt this stuff. We're taking it like whatever exported serialized format is in the game, translating it by some logical world position that we assign to it in the simulation, then rotating and translating all of that so it's relative to the camera's position rather than to the world origin, and then applying a perspective transform so we can crunch everything down into screen space, right? And we're trying to do all of those things in something that is as mathematically cheap as possible that requires the least amount of repeated work. So what we don't want to do is iterate over every single vertex and divide it by its z-value. Well, we will actually do that division, but we also have to do some other kind of multiplication, that kind of thing. We want to make it as cheap as possible. Is basically the idea. So a perspective transform matrix is actually in 4 dimensions. And why it's in 4 dimensions is not super obvious, but let me actually dig out the mathematical expression.
Sam, I'm looking this up for myself too.
Yeah. Here we go. The perspective transform. Okay, here we go. So, I like to draw my matrices like this. Technically, usually, like you're supposed to do this, but I find that a little bit too verbose. You know what? Why be a rebel? I'll do it the way that everybody's familiar with it. We're going to be introducing a ton of new terminology. That I'm going to try to hand wave away. That is your perspective transform matrix. I'll explain what the terms are. But what you're going to do is you're going to multiply it by your vertex's x, y, and z coordinates, and you're going to throw a 1 at the end there just for kicks. Right. So why did we go to 4 dimensions? Well, let's actually multiply this all out. It's going to be a little bit painful, but bear with me here, right? Do we remember how to do matrix multiplication? It's actually for loops, right? We're going to take this first row and then multiply it component-wise by this thing here, right? That's what our matrix multiplication is like.
Mm-hmm.
And what that's going to give us is, d over a times x. And then it's easy now. We've got a bunch of zeros, right? So
Yep.
So that's all that first term is, right? The next term, we got 0 times x, which is 0, plus d times y, right? And then we got a bunch of zeros, so that's all that second term is.
Mm-hmm.
And then we got a bunch of like crazy stuff here. It'll basically end up looking like this. N plus f plus 2nf over n minus f all times z. Oh, no, wait. No, this is wrong. I'm actually forgetting where the z is going here. It's actually z times n plus f plus 2nf divided by n minus f. And then this next one is interesting. This bottom row, we get 0 times x, 0 times y, negative 1 times z, so we got negative z here, and that's it, right?
Mm-hmm. Wait. Oh, interesting. Okay. Yeah. Okay, I see it. Sure.
Okay. Huh. So let's actually imagine that we're dealing with a square screen, right? The screen is totally square. What this letter A? I introduced the letter A, and that's like, well, what the hell is letter A, right? Is that even visible? It's not visible.
No, yellow's too yellow.
Yellow is too yellow. Okay. That's new. That is our aspect ratio. Okay.
Mm-hmm.
I will explain why aspect ratio matters in a second. But let's just pretend we have a square screen.
Right? As I say, we crossed into that actually in the first 3D stream where we had to adjust by aspect ratio to even draw the square.
That's exactly right. Because essentially, like the screen that we're actually drawing into is basically in unit. It's basically the x and y axes are the same size regardless of the aspect ratio, right? But let's just pretend, for the sake of simplicity, that our screen is square, so a is 1, right? So that's actually kind of promising because we have d times x and d times y, which if you scroll up, is starting to look a little bit like our screen space coordinates. Like if you scroll up on the whiteboard, on this, there you go. We do have, s sub y2 is equal to y sub 2 times d, right? We got a piece of that there. We also have x sub 2, s sub x sub 2. The screen space position of the x coordinate is the world space position of the x coordinate times d, and then with a division. And we're kind of halfway there, right? If you look down at the projection, the result of that projection multiplication, we're kind of halfway there if the aspect ratio is 1, right?
Yep.
And then we have some really complicated thing for the the resulting z coordinate. We don't need to get too much into what this z. It is actually used for 3D rendering, that really complex looking z coordinate. Actually, I will explain in terms of clipping. We talked about clip space. I'll talk a little bit about that. And then we have this interesting value negative z down there. Remember how in OpenGL z coordinates are actually negative when they're in front of the camera?
Right. Yeah.
If you negate that, what you're actually doing is you're saying, what is the absolute distance from the focal point, right? As long as that point, if that point is in front of the camera, then negative z will actually be positive in the OpenGL space, right? Now, that's not every 3D system works that way. Actually, Direct3D, which is Microsoft's competing API, has a positive z-axis going out. So the actual projection matrix actually looks a little bit different in Direct3D, which is fun.
Interesting.
Yeah. Okay. So so this is what we call the, oops. This thing here, keep not changing the color. This is the clip space coordinate. And basically, what we can basically say from this is if each of x, y, and z is in the range -1 to 1.
Mhm.
Actually, I should be very, very clear about what clip space coordinates actually do. We call this a clip space
Interesting.
coordinate. So this is actually the W coordinate. This is x, y, z, w.
Mhm.
So the clip space coordinate is 4-dimensional, but it kind of looks like a 3-dimensional coordinate, but with this extra thing hanging on. And what we do with the extra thing is we basically use that to determine whether something is visible or not. So the reason why this is called the clip space coordinate is that if we can use this coordinate to determine whether we should clip a vertex or not. And when I say clip, that means to actually remove it from rendering. Does that make sense?
Yeah.
Yeah. Okay. So this is literally what your graphics card would do. Like your graphics card, like this matrix, this 4-dimensional coordinate, which I think is called GL position in the shaders,
Yes.
is going to go into this fixed thing that you don't control, where it'll say like, okay, I'm going to compare each of the x, y, and z coordinates to the w coordinate, and if they fall into the range -w to w, then I'm going to keep it, and if it's not there, I'm going to chuck it. Okay. And then the next thing it does, as part of its like automatic built-in functionality, is what is called the perspective divide. Which is divide x, y, and z by w.
Okay.
So what is the value of w
Interesting.
actually?
I mean, it's the original z coordinate.
It's the original z coordinate, but essentially the absolute value of it if it's in front of the. And so
Right,
the division is what actually gets us the division that we were looking for, right? You know how we were talking about how like you can never get to a division through linear algebra through like matrix transforms. But you can just make division like outside of the matrix transform as long as you preserve the value that you're trying to divide by somehow.
Gotcha.
Yeah. So you basically this is their way of basically encoding the thing that we need to divide by, keeping it in the pipeline. So essentially, we basically through the matrix math, we've carved out this extra little space where we're trying to preserve the original z value, and we preserve it because that at some point in the pipeline, there's going to be a piece of hardware that says, okay, I'm going to take that original z value, which is actually now in the w coordinate, and divide the x coordinate, the y coordinate, and the z coordinate by that value, and that's my screen space position, right? Yeah.
Oh man. That's very clever. So I assume there's just some special hardware that's just like something's primed to divide a bunch of values at the very end.
Yes.
And that's it.
So whether it happens in hardware or whether it just, I mean, it has to happen in hardware on a GPU because there's like the vertex shader happens in hardware and the fragment shader happens in hardware. And it's not like the stuff that happens in between them goes back to the CPU. So it's happening in the hardware somewhere. You just don't get to program that, right?
That's so cool.
Now,
Okay.
you could have a software rasterizer or software 3D renderer that does all of this stuff on the CPU side. But generally speaking, even if that's the case, the 3D API will not expose this stuff to you. So it's not like OpenGL like exposes this to you. It just tells you, okay, that's what's going to happen, right?
Right.
And it's kind of counterintuitive because it seems like a very, very specific thing to do this clipping, both this clipping and the division, when you're given so much control over everything else, right? You're like, you can basically like completely customize the vertex shader, you completely customize the fragment shader. And yet the built-in clipping and division is just assumed to be the thing that everybody wants to do, to the point that it's just like really built into the assumption there. It's just, it always struck me as surprising because like, what if you didn't want to do that and you wanted to do something really crazy and weird, like simulate physics or like mine Bitcoin or whatever? Doesn't this get in the way of doing all that stuff?
Does the rise of like the general purpose GPUs sort of, are there ways around this now? Is that what the trend is? Is that the difference?
I have no idea, actually.
Okay.
I think there are different APIs to talk to this stuff. And indeed, like it could be the case that what we think of, what I described as being a hardware operation, this clipping operation and then perspective divide, may actually be something that the shader compiler just tacks on to the end of the vertex shader, right? Because the shader compiler is just compiling something down to assembly. It's just assembly that doesn't run, or machine code really. It's just machine code that doesn't run on the CPU, it runs on the GPU, right? So it still could be the driver that's doing this. I wish I knew. I kind of think that it's hardware accelerated though, because it's like, since it's so common, wouldn't you want the hardware to just already have this there? You know,
Yep.
Why have machine code do it, right?
Well, I bet the vertex, the compiler could add the instruction to the shader, but then whatever's running the vertex, like that instruction is just happens on the GPU really fast.
Yeah. I guess what I'm saying is it'd be nice to have an ASIC to do this, right? Just the same way that it's nice to have an ASIC to do SHA-256 so that you can mine Bitcoin, right? Okay, so you can see that like this really complex construction was designed not only to get us the screen space coordinates, but it's also there to help us decide what is visible and what is not. It does this clipping operation that comes in with it. And notice it's also clipping on the Z dimension as well. So the notion is that there is actually a field of the Z coordinate, or the range of the Z dimension, where something is visible, and outside that range it's not. And we didn't actually talk about that. Like if we scroll up, basically this drawing would imply that things at infinite distance are still visible, right?
Right.
But that is not actually what our 3D system actually does. So what happens is that there is an implied near field and an implied far field. I'm going to draw it here. Huh. That's weird. It's behaving a little bit differently than what I... oh, there we go. It's because I'm left-handed.
Nothing's made for us lefties.
I forgot that you're left-handed, Dom.
I know. That's all us cool kids are.
Oh, did I make it the same color as the other thing?
And I've seen this shape before, which is interesting. I've seen the like sort of
it kind of looks like your camera. It looks like your camera, right?
It actually does look a lot like a camera, yeah.
Yeah. How did this come up? Why don't I just... what you have seen is like a truncated parallelepiped. I think you started to draw. It looks kind of like this.
Yep, exactly.
Right. The other term for this is the frustum. This is what's known as the view frustum.
I was wondering when the word frustum would show up.
Yes. So in practice, there are two planes that we haven't mentioned before. We have the near plane and the far plane, which basically form our view frustum along with the planes above and below. And
I
the frames
I
on the
saw
left and
NNF
right.
show up earlier.
Yes, there you go.
Very clever.
Yes, and you notice when we multiply it all out, see that clip space coordinate?
Mm-hmm.
It actually kind of makes sense that N and F only factor into the Z coordinate because we're basically trying to decide whether it clips along the Z dimension, right? So they really only should matter if it's really the only position that should matter from the perspective of clipping along the Z dimension is essentially the Z position and then the near plane and far plane values. And N and F are essentially the distance from the focal point of the near plane and the distance from the focal point of the far plane. What I'll call out here is that the near plane and the focal length are different values, right?
Yeah, well, right. D is the focal length, N is the near plane, and it's sitting in front of the focal length.
Mm-hmm. So the reason why they do that is that if there's something like literally right in front of the screen, it would obscure everything. And so there's a notion in a lot of 3D graphics, or like we play a game, right? What happens when you get really close to an object?
Right, yeah, it like disappears in front of you. That makes sense.
What a lot of games will do is actually start to fade that object, but the fading is optional. And the reason why they fade is that at some point it's gonna disappear completely. And they'd rather have that be a smooth transition than a pop, right?
Yep.
And the way that they get rid of the pop, because you get the pop once it hits the near plane, right? Once it hits the near plane, it disappears because it gets clipped.
I've seen that character walks too close to you and suddenly you're looking inside of them experience.
Yes, exactly. On the far plane, they don't do fading, but at least in older games, you would do this thing called fog, where basically, like, I don't know if you ever played N64.
Oh yeah, yeah.
But N64 had I don't really know where it was deficient. I think its fill rate was really bad, so it couldn't draw that many pixels onto the screen or something like that. But like N64 was notorious for having a very, very close far plane, right? And therefore the fog was really close, right? And so every game seemed like it was like just fog
strangely
right?
claustrophobic. Yeah.
GoldenEye was like that. Turok Dinosaur Hunter was like that. So many games basically had really, really close fog, right?
Yeah. Weirdly, I don't recall that in Mario. And I think it maybe was just done in a way. But it was like the tech demo for the 64, right?
Yeah. So Mario 64, they actually succeeded in not making it Fog City, and I couldn't claim to know why that was the case. I guess the textures in Mario seemed a little bit more simple than some of the other
and the models too. Everything is really low poly count.
Yeah. Okay, so that's what the N and F are.
Now, why? So negative W to W here, though. Isn't that scaled based on the original Z coordinate?
It is. Yes.
Okay.
Yeah. So it's different for every point.
It's different for every point.
So another way that you could think of this is that if we did the clipping after the perspective divide, that would be fine too. Because if you scroll down to that sentence, if each of x, y, z is in the negative w to w range, then the point is visible. If instead we did the perspective divide, that sentence would read x over w, y over w, z over w is in between -1 and 1. That's the same sentence, right?
Okay, great.
Yeah.
Great. Okay, so essentially everything, even z, is scoped down to this -1 to 1, left to right, up to down, near to far, as our sort of coordinate space at the end of the day.
Exactly. It basically says that if you're in between -1 and 1 after the perspective divide along all three coordinates, you are somewhere inside the view frustum. Right.
Gotcha. Okay.
That's basically what we're saying.
Weird. All right. I love it.
Yeah, it's pretty weird.
It's very weird.
Yes. Okay. what is the other interesting point that we can make? We talked a little bit about okay, so this gives us a coordinate for vertices, right? We have essentially we get vertex positions. Last stream we talked a lot about the fragment shader though, right? And the fragment shader doesn't just render vertices; it renders all the stuff in between the vertices, right? And so we need a way of determining perspective correct interpolation of values. Like remember, every vertex has a bunch of attributes. One of the attributes is the position, one of them is the normal, one of them is the texture coordinate.
Right.
And we wanted to make sure that we were scaling them in a perspective correct way, right? And
is it not applying the same transform to everything? Is there a different transform?
It is exactly it is conceptually applying the exact same transform to everything. Mathematically, it doesn't actually do that. It uses some numerical technique called forward differencing because it's actually kind of hard to. I guess it's expensive to do the brute force method of calculating perspective correct interpolated values, and so it uses some incremental thing. It's basically a hack that's like almost precise. Suffice to say that even the hack is expensive to the point that like we talked about how PlayStation 1 didn't even have it at all, right?
Yep.
They used some other hack and they just did some funny version of that doesn't quite look correct, right?
Interesting.
Yeah. Once again, the graphics API assumes that you always want perspective correct stuff. And in fact, let me see if I can't find, I don't remember what it's called off the top of my head, but I'm going to look up in OpenGL what it's called if you don't want perspective correct interpolation.
Can you turn it off? That's an option.
Yes.
That's great.
Per attribute.
Per attribute.
Yes. Yes. If you Google OpenGL no perspective, but there's the no perspective is all one word, or GLSL no perspective, you'll get an example of that. The no perspective is all one word. Okay, yeah, the first one is that first link will work.
Great.
Yeah. So basically, yeah, there you go. These are qualifiers in front of in a shader. What are the inputs called? Do they just call them ins? Do they just do like in vec3 or something like that? Do you remember what it was?
In one version it was in, but for the other it was like their attributes, right?
Their attributes for the fragment shader. Yeah. You basically prefix that with flat, no perspective, or smooth. It's like const or non-const, or like how like some languages have modifiers for variable declarations.
Totally.
The default is smooth, and smooth in the modern day the default is smooth, and that means that it's going to be interpolated in a perspective correct way. No perspective means it's actually interpolated in screen space, which means it's not accounting for the fact. It assumes that the triangle that is drawn to the screen is flat in world space, or like basically like completely.
I mean, would this be how you would draw like a HUD on top of the screen? Like you don't want that to be skewed at all.
Correct.
So you could just draw a rectangle at the near plane too, and that would work though.
Yeah. But a HUD would also be in world space probably represented with a z, like with equal z values. So if you did it in smooth or no perspective, you'd actually end up with the same result, right?
Interesting.
And HUDs, like oftentimes with like things like HUDs or your GUI or your health bar and that kind of thing, you'll often draw those in what's known as orthographic projection, so not perspective projection. And orthographic projection doesn't do that camera model that we were talking about. So if we scroll up, or actually, I'll just do a quick sketch of what ortho projection does. Ortho projection is you have your eye, you have your focal point, you have an object, and you have your plane of projection, and the light all goes this way. It doesn't skew towards the focal point. And in fact, the focal point's kind of irrelevant at this point. You don't really need it.
Gotcha. Yeah, that makes sense.
And that's basically an orthographic projection. Isometric is a variation on this, where everything's kind of rotated, but you still don't actually. There's no foreshortening in isometric.
Right. The parallel lines never converge. Yeah.
Exactly. So there's no division anymore there. Yeah. So an orthoprojection is actually what we're doing in Manchester right now. Like, you can think of like all the graphics that we're doing is an orthographic projection.
It's beautiful.
Yes. Which is actually why we don't differentiate between view space and screen space. Like, a lot of our matrices, they do like a world to view, and then they just render them straight out, because there's no perspective transform between the view transform and the screen transform. There's nothing in between.
Interesting.
That matters. Yeah.
Huh. Okay.
Okay.
Man.
That was a lot. What questions can we go over? And we'll see what I don't know about. We'll see the limits of my knowledge here.
We've got everything. We are drawing. We're drawing like in the -1-to-1 space right now explicitly.
Yes.
Nothing. The camera can't move. Nothing can exist outside of this. The camera can't follow the player.
Yeah, and in fact, the code that we're writing actually does do a perspective divide. It's doing all that stuff. It's just that our perspective is, I believe, our z values are 1 or something like that, right?
Mm-hmm. Oh yeah, in our shader, our z is 0, our w is 1. Yeah.
Yes. Okay, so let's try something interesting. Let's actually set the z value to something whose absolute value is greater than the w value, because that should actually clip you, right? Remember how we talked about clipping in the view frustum?
Interesting. Yeah. Yep. So that should just pop it off the screen when this reloads. Indeed, it does.
Yeah. And if you set it to exactly 1, I believe it should still show up. It should appear. But if you set it to 1.1, it should disappear.
So interesting. Okay. Yep. All right. That makes sense.
When we first were playing with this, I kept asking the question, well, why does it disappear? Why does it are we doing backface culling? Is there something else that's going on? I did some reading, and it turns out it's just the view. It's just typical. It's the standard view frustum clipping. Which you can think of as the most basic form of clipping that you can do.
Nice.
Yeah.
Huh. Okay, so if we wanted to set up a camera, we essentially need to come up with some. Let's see. So the camera can move around. Do we? Okay. Oh boy. Okay, so we define a camera, we define these values, and then we drop it in there as a 4D matrix that gets multiplied by the point, and then we have perspective. I can almost wrap my head around this.
Yeah, and it actually turns out that the OpenGL API, or actually probably GL matrix as well, the library we use for math, they probably have a perspective matrix function. Where you give it the focal length, you give it the aspect ratio, you give it the near field, you give it the far field, and it just spits out that 4-dimensional matrix for you.
I bet you're right. Yep.
Yeah.
Yep. Oh, clever.
And they also have an ortho one as well.
Very cool.
Yeah.
Oh, I see. In perspective from, you can do NF and field of view, or a more specific one. Yeah. Okay.
FOV and aspect ratio are roughly equivalent to each other. Mm-hmm. Or rather, FOV. Wait, where does FOV come into play? FOV is the
up, down, left, right.
It's the focal length. Focal length and field of view are related to each other.
Why is it 4 numbers here then?
For an ortho projection, or I'm talking about for the perspective projection.
They're saying FOV is a object with 4 values as well. Up, down, left, and right degrees.
That's a little bit different. I was talking about on line 1268. This is line 1268 is the more basic perspective.
Oh, frustum.
Yeah.
I see.
This one here.
Oh no, that's what I'm saying though. FOV still has 4 values.
Not the function above it.
Okay. Yeah, frustum. That makes sense.
Yeah,
vertical field of view radiance. Yeah. Okay, yeah, that I like totally.
Yeah, that is equivalent to the focal length, because if you assume that the plane of projection is a fixed size, the vertical field of view is going to grow larger or smaller depending on how far away that plane is, right?
That makes sense.
Yeah.
Oh yeah, this is for the WebVR API.
Okay. Oh.
Where I guess up, down, left, right actually might be meaningful in that sort of sense for a different projection that needs to wrap.
Oh, right. And I wonder if the view frustums are a slightly different shape for VR.
Mm-hmm.
I don't actually know.
VR view frustum shape. Yeah, but that seems like a question that someone can answer for us.
I mean, maybe not. Because they're like theoretically the model should the sort of like the theoretical model should be identical. They're both eyeballs. They both have their planes of projection. They both have light rays going in, right?
That's true. Well, I think the distinction is that maybe it's just a much wider field of view, because it seems like all this is modeling a camera with like a square versus modeling like this sort of spherical vision that we have.
Oh, I wouldn't call that a perspective projection at that point, though. If the mathematics change dramatically, because my understanding of what our eyes see is essentially, if you close your eye, it's just like it's just one 3D rendered view, and then if you have both eyes, what's happening is, well, your VR headset's just showing you two slightly different 3D rendered worlds, right? It just renders the scene twice. You have two cameras. The cameras are separated by a couple inches and slightly angled, something like that.
Mm-hmm. Yeah,
or not even angled at all. They're both looking forward.
Both looking forward, yeah. Regardless, I guess we don't have to deal with this one or with these, since this definitely looks correct. That's cool.
Cool. So the perspective projection, I believe, is usually conveyed into the vertex shader through a uniform.
Yeah. And would we do the perspective and the world projection there? Yeah. Or world transform?
Yeah. And then model and view oftentimes are combined together into the same uniform as well. I don't know why. Like, you could probably just combine them all into one giant thing if they're always the same. Your projection matrix is going to be constant unless you start messing with the FOV value, in the control in the settings. Your view matrix is going to be the same for every frame. So, because like the camera is basically in a fixed position every frame, so it's going to be the same across all of your geometry. And then your world and model, your world matrix transform is going to change from entity to entity, right? Because they just have a different transform. And then your model your model position is just going to change vertex by vertex, right? Yeah.
Mm-hmm.
So how you actually shove those into the shader, and like which ones you pre-combine in the CPU, like pre-multiplied in the CPU and then set as a uniform into the shader, like I think it can depend on what you're trying to do.
Mm-hmm. Yeah. Interesting. Okay.
Yeah.
Wild.
So we've blown our minds with the math of 3D graphics.
Do you want to try to put it in here?
Yeah, we can try to, like, maybe the thing to do is to start with a cube. Or you could even do a triangle. We need some way of conveying depth.
Right.
And if we do a cube, we need like every face to be a different color in order for us to actually notice. Otherwise, it's going to kind of look like a weird octagon, you know, if it's all the same color on every face.
Right. Right.
Yeah.
Let's see. We're doing aspect here.
Yeah.
But actually, I think we take that out of our positions now, don't we? This becomes more part of the.
Yeah. And then if you don't want to wait for the compile to happen every single time, one thing we could do is just make a quick little HTML file that has like a lot of the stuff in it, and then mess with that for a little while, and then
parcel it up. Yeah, that seems good.
Yeah, it doesn't even need to be parcel. I mean, we could just do an HTML file with some JavaScript in it if we wanted to. It wouldn't be TypeScript though. That's the only trick. I think you can do TypeScript transform if you include the TypeScript. Like, if you include TypeScript via CDN, I bet you could set the script type to TypeScript. And it'll transform at runtime.
You're totally right. Yeah.
Or do we need Babel? I don't remember how this works.
I think there's a CDN for it. I've seen including script TypeScript on the page, but yeah. If I can't find it on this one, I'm not going to do it. Yeah, it looks like a lot of Babel. Let's just write HTML, whatever.
Okay. So we'll just do it in JavaScript, and it won't be TypeScript for now. Is that okay?
Yeah. That is extremely
And
okay.
we can CDN like GL matrix or something like that if we wanted to do the math.
Yep, that seems. Oh yeah, we'll probably want that. Okay.
Yeah. And then what we can also do is grab. Although I think that the GL context has all the math we might want to need. We might want to use. And we can also grab stuff. We can borrow a lot from WebGL2 Fundamentals.com, which we went through last stream, right? They've got a lot of setup. They've got the vertices set up for us already.
Mm-hmm.
We can borrow at least the model.
Is it this site?
They had a state diagram, or a state visualizer.
Yeah, was that?
Do you like this background or what?
I'm super impressed, and also that's one of the most performant WebGL things I've seen. So, yeah, I absolutely love it.
Maybe WebGL2 state visualizer. Maybe that's the thing that we.
Yeah, where did you find that site? I thought it was WebGL2 Fundamentals. Do I need to, do we even have the old show notes up yet?
We do. Let me see if I can find it. WebGL state. It's so funny how maybe it was OpenGL state, but it was WebGL2 specifically, right?
Hmm.
It's so funny how like we totally just can't find it anymore.
Did it even exist?
Or did we just imagine it too?
Yeah, what happened on the last stream? I won't even be logged in this browser. Oh man, there are some great WebGL backgrounds going on here though.
Oh, you know what? The show notes for the last show aren't up yet, so I don't even have the link to that anymore. Let me look in our Slack and see if I can find it. This is hilarious.
It's cool. I'm just finding the tiny WebGL helper library, which is actually pretty cool.
WebGL state diagram. And it is part of that website. Maybe we want the WebGL2 version of that. So I bet if you just put that into the URL, it'll. Oh, nice.
Hilarious. So we've got our cube.
Yeah. And this cube is actually this VAO is actually more complicated than what we need because we're not going to have vertex attributes, presumably.
Mm-hmm.
We're not going to do any lighting multiplication or anything like that. We're just going to have vertex colors, I think.
Yep. And so going back to their vertex shader, there we go. Projection, model view, and position. Position is the input, and model view is it's I see. It's the uniform for. Oh, okay. It's because we want to draw a square. We want to draw every model's coordinates are around its own origin, and we're just changing the draw point on the screen. Okay.
Yeah.
Sure. Oh, lordy. So, I mean, I could copy this into an HTML file.
Yeah, we could copy it or copy it piecemeal and take what we need.
I say we need a lot. We're going to need a lot of our that canvas. And then we're going to need a big old script tag.
Can you put a script tag outside of the body?
Yeah.
Is that a routine thing to do?
Thought so. Why you gotta put it in the body? It's usually in the head, so.
I'm sure it's fine. I'm sure the browser will do it. I've always thought of stuff having to be in the head or the body. No exceptions. But
I put stuff after the body that I want to be the late loading thing.
Sweet.
Yeah, you're right though.
I'm into
I don't know why that's what's in my head. So let's see. Canvas equals document dot get element by tag name canvas.
And does that always take the first one, or does that give you a list?
I think get element should give you
a single one.
The first one.
Okay.
There's a query by that gives you all of them. But
get element by get elements by tag name.
Okay. Is there a get element? All right.
You could give an ID and do get element by ID.
Yeah, I could also just do this.
Cool. I'm into it.
Yeah. Okay, cool. So this will. Oh my gosh. Got our context. Probably don't need a bang anymore. Let's grab these suckers. All right, still running. That's good.
Yeah.
I actually expect that all of this will work.
We want it to be a little bit more closer to the example. We could rename the CTX variable to GL, and that'll make it easier it'll make it a little bit more compatible with what's in the example. Yeah.
Sounds good to me. Though we have. Oh, and that works here. Gotcha. Right, because.
Okay. Oh, that was a really useful error message. I'm shocked.
Can't use
exclamation point is only for TypeScript. Wow.
I agree.
VS Code. I'm impressed. Good work, Microsoft.
If anything's going to get TypeScript right, it's VS Code. But yeah, duly impressed. Props to them. Okay, so we'll do our clear. Oh, and everything that's this up CTX is still.
Sorry, I feel like I've ruined us.
Nah, it's worth it. Okay, there's our canvas.
Nice. Yeah. We've got a border. We've got a padding or a margin.
Body has a default margin. Yeah.
Okay.
We can include normalize in a second. So let's see. So okay, we've used the program. So
CSS is so complicated.
what part of my brain is wasted on the knowledge that that's always there?
Yeah, I don't know. I actually have a little bit of or a lot of CSS imposter syndrome, where it's just like there's so much that I don't know.
There's frankly too much that I know.
Yeah.
I wish I knew less about it. Okay, cool. We link the program. We use the program. And yeah, so you were suggesting let's take some positions from here, and I think that's a great idea. Yikes, there's a lot of points.
Yeah.
We're not doing any texture coordinates. We are going to need the vertex indices, though. Because that's how this one works. And I guess we'll need to... Oh, we haven't set up the vertex array yet, but we will.
Yeah.
Okay. This all looks very pleasantly familiar from last time.
Yeah. We don't have a texture, so we can either do vertex colors or we can make a texture.
I was gonna go with just straight colors for now because I feel like perspective is gonna give us enough of a yeah, that sounds hard enough.
Yeah. So if we do colors, we're gonna need a new 24 element array of the colors. Does that make sense? Or even
more, right?
There are 4 vertices per face. So there's 24 vertices times 4 numbers per color, right? So that'd be pretty big.
Yeah, and we can get away with 3 numbers per color, but yeah.
Or yeah, 1 number per color, and it's just how much red it has.
That's not an unconvincing
right?
idea. Yeah. So let's see. We've got our cube vertex array. I just want to make sure I'm doing the buffer stuff right. We bind the array buffer. We put the buffer data in there.
Yep.
Okay.
And then for the indices, we need to bind the array, the element array buffer, which I think is maybe a little bit below there.
That's right.
I'm so glad we went over this last week. I feel like I learned so much just even stepping through that.
Yeah, dude, it was really, really helpful.
Yeah.
There we go. Okay, so we're right. Great. Okay, so we're, oh boy. Why does the vertex shader specifies a color? Why is that?
That's the vertex color.
Oh, right. I see. And so it just gets passed through to the fragment shader.
It just gets passed through the fragment shader. Exactly.
Right. Okay. Okay, so we do need to get the a vertex color attribute. Yeah. Oh, but do we not? Crap. The loading the attributes part. Oh, here we go. Position lock. Where did position lock come from? We didn't get it. Hey. Got that. And let's see. These are different. So this is a vertex position. This is a vertex color.
And then PRG is the word program, I think. Just the variable name is.
Yeah, thank you.
Yep.
That's the only place we use that, right? Yeah, because you just use that to get stuff out of the program. That's actually clever. Okay, so then the thing that's going to change here is that we're going to have our color buffer.
Mm-hmm.
And it goes into the color location. And now we get to decide. So we're going to say that it's one component per iteration.
Mm-hmm.
And everything else is fine.
And then we need to actually create that buffer, which I think is also a float 32 array, but it's only going to have 24 elements. I think colors are all 0 to 1. Is that right?
If we make them float, which they probably are, yeah.
It would just be vertex colors. Or Q vertex colors is what the variable would be. Yeah.
If it's just 0 to 1, oh boy. So now we figure out what order the points are in for this to make any sense.
As long as they're all different colors, I think we can see we're going to be able to see it. I think.
Okay.
So we could do like 1 divided by 24, 2 divided by 24, 3 divided by 24, all the way to 20.
That's gonna be weird. I love it.
Yeah. And you're right to say that knowing what order the verts are in does matter to this if we wanted to like gradually increase the intensity or something like that.
Or I mean, if we wanted to draw faces of different colors, of different intensities, right now we're a little SOL.
You can see how untenable manually creating geometry becomes. Like even just doing a cube.
Oh yeah. This clearly needs to be clearly needs to be automated and generated in some way.
Yeah.
At some point, we'll load a model file, and that'll be great.
Yeah.
Cool.
And then I think our shader needs to be updated so that this is no longer vec3. Although before, didn't we observe that when we injected a 2-dimensional vector in, it just like 0 filled it and like automatically expanded it?
Yeah, that's true.
But that's weird. I'd rather have that directly reflect the literal data that's coming in through the.
Yeah.
Yeah.
I agree with that.
Okay.
I'm curious if float is actually gonna. Oh boy. That's such a strange error to have thrown for that. All right, well, it compiled, so that's...
compiled, okay.
That's something, yeah.
Nice.
Okay, so I guess the thing... So now we need to... so we've done that. They bound it to null, did all their stuff. We're not going to do any of that. We're already using the program, right? Why did they use it twice? I guess it's just like it's rendering code. Oh, maybe they didn't use it twice, actually. Nope. All right. Let's put it down here then.
Yeah.
Render. Oh, I see. I took some of our code for this. That's why.
Got it.
Got that. We've got the clear. Do we want depth test and call face probably?
Yeah.
For this we do because we actually care about
we don't want to draw the surfaces that are like the rear facing. Although the depth, that depth test will take care of that for us. Yeah.
Yep. Though I do want to turn it off and see what's going on because that sounds pretty cool too.
It sounds pretty fun. I bet if people draw elements right now, you'd get something drawn and it'd be really weird.
I think I just want to do that.
Yeah. You might have to set some uniforms, but do we have any uniforms?
No, we don't because we're using our vertex shader. So,
and then the number of triangles is not 36; it's 24.
I took theirs. I think it's 36.
That's 36.
Why?
Oh,
I know what you're saying.
It's 36. It's 36 elements because there's 36 elements in the index buffer, in the element array buffer.
Right. Yep. There you go.
But the data, remember that each vertex is used. Well, a couple of the vertices on each face is used twice. So that's why there's only 24 data points for the colors and the positions.
Yeah, that makes sense. So when I turn off depth test, I see different colors.
Yeah.
That's the extent of it.
So this actually kind of makes sense. What we're seeing is that we're seeing a non-aspect ratio adjusted like single face of a cube.
Right, and everything here is 1 to -1, so it's filling the canvas perfectly.
I would expect slightly different shades of red. Honestly,
I think they are.
Okay, maybe I can't tell.
Yeah, here I have a idea for this one actually.
Yes, gonna do a for loop.
No, I was just gonna do. Whoops. Uh, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
Oh, okay. They need to be a float 32 array, but
oh yeah. Oh, and
it
it's
worked,
more
though.
than.
It totally worked though.
Yeah, you. That's what I wanted to see. Okay, cool.
Oh, that's really cool. Yeah, oh, it's basically black and red.
Black and red alternating on vertices, which is maybe nonsensical, but at least we can see it.
Yeah.
And when I change it, it reverses. So sure, that checks out.
Yep.
Okay.
But this all makes sense so far, which is great, right? We're not getting anything that's nonsensical.
That's the weirdest fucking part, is that I understand what's happening. Yeah. So let's get our perspective in here.
Yeah.
So what is this M4 they're using?
M4. Where does that come from? Good question.
Yeah.
Is that 3JS maybe?
I'm surprised by that.
Let me see if I don't think it comes with MDN. I found a link to a JavaScript M4 macro processor. Boy, talk about the old and the new combined together.
That's amazing. I'm inclined to M4 is not defined.
You can you can CDN GL matrix or something like that.
Yeah, I think that's gonna be the easiest thing to do here.
Yeah. Man, 3.js is heavyweight. Holy crap.
Yep.
I can't believe you've been willing to go along with me about writing everything from the ground up. I'm grateful, but
well, I've learned a lot.
Yeah.
I like the
idea that we're
I can dig around in Unity.
Yeah, yeah, exactly. I like that we're demystifying a lot of this stuff, because I feel like part of it is just like wanting to know how it works, right? I'm
gonna feel really empowered to dig around in Unity after we do this too, because like now I understand the strange shit that they throw at you, which is wonderful. Yeah, I really want to know where this dude's getting his M4 from, but I guess it doesn't matter.
Yeah, I don't think it exists I don't think it's part of like the standard library for sure. Weird. But we have GL matrix, right?
Darn tootin'. Okay. So let's see. I want to look at the uniforms that they're dropping in here. So the projection and the model view.
Yeah.
I expect this to. Maybe it doesn't care since I'm not using them.
Yeah, or they get default values if you don't provide them.
They get default values. Well, let's see. Yeah, right, because it's 0, 0. Everything else zeroed out when it was cool. Okay. So projection times 0. Projection of 0, surprisingly. I think it zeroed at every coordinate. It multiplied everything and
Oh, so you're just basically getting points. It's like you're collapsing all the geometry into a point,
right.
which is not going
It's
to
all
render.
it's all at 0, 0 somewhere.
Yeah. It's an infinitesimal volume.
Mm-hmm. Okay, so let's just look at this in our code for a second. Where would we set uniforms actually? Is this after you use the program? It is.
I would, yeah, yeah, definitely. After you use the program.
Okay, so this is like, right, it's like part of our rendering. It's
code,
like,
yeah. Although the perspective matrix itself, probably you can define in your setup, and it's almost, well, it'll change. The reason, let me tell you why it will change within the same tick. Because you're rendering UI, right? When you render UI, you probably don't have. You might change your. Well, I don't know. You can still save the game view projection matrix somewhere in your game object, right? That will probably never change. But you will change the uniform. You will change shaders when you're drawing the UI.
Gotcha. Okay. All right. So let's do equals. This is mat4.custom.
Mat4.perspective, I think it's called.
Well, that was the. I mean, geomatrix mat4. That's what I thought was so weird. Was that the perspective? Oh, was I just reading the document backwards? I was reading the document backwards. I'm sorry.
Oh, okay. No problem.
Explains why we were saying two different things, though.
Yeah.
Mat4.create, my old friend.
Yeah.
Okay, so vertical field of view in radians.
C pi over t. Well, what is geomatrix doing? Or sorry, what is the example doing? I'm sure they're using a similar API here.
That's a great question.
They're doing a 60-degree. They're doing 60 degrees. That's cool. I usually hear 90, but I don't know. What do you set your FOV at when you play games?
120. I got to see everything.
Oh, I like it.
More advantage from more playfield. No, I actually keep it like I just do 70. I think.
Really? Wow, that's really narrow.
It is, but I feel.
Does it make you seasick?
I think too big makes me feel like I'm like, yeah, I'm moving too quickly or something. I don't like it.
Yeah.
Okay.
And then the next one is the
aspect ratio.
Yeah.
Okay, cool. That's GL dot or canvas dot width, canvas dot height.
Divided.
Oh.
Yeah.
Thank you. Yep. And then near.
No,
I see. So
both those values are fine. Yeah. Everything is like 1, -1, right?
Mm-hmm.
So I expect this to not draw anything or to clip off pieces of the cube because we haven't applied the model view transform yet. And so the camera is currently at the world origin, and the cube without the model view transform surrounds the world origin. So if you take off base culling, you'll see something, but I think as it is right now, we won't see anything.
Lock. I need to grab the.
You need to grab the uniform.
Is it? It's get uniform location. Yeah. Program and.
Is that what the variable name is called? Projection lock. You scroll up, in this shader. What do we call it in the shader?
Oh, in the shader. Thank you. Just projection.
Okay. Yeah.
Yeah, that makes sense. Okay. Nothing.
If we turn off base culling.
Yeah, that's what I'm gonna do next.
Yeah.
Still nothing, surprisingly.
Yeah, that's a little bit surprising to me.
Yeah, let's information protection lock. Console.log. Rejection. I mean, that's probably fine.
Mm-hmm. Looks good.
Huh. Okay.
Although I would have expected that -1 to be. It might be because this is doing like this might be doing column major rather than row major.
Oh.
I can't. But it's GL matrix, so it should be using whatever GL expects.
I was gonna say it's yeah. I'd be surprised if it messed that up.
Yeah.
Let's get model view in here too, at least.
Oh, I see one issue.
Yeah.
On line 24, we're setting the Z position to 0 at all times. We shouldn't be doing that.
Okay. Right.
That should be a vec3 vertex position. Because we had been drawing in 2D before, but we should be.
Oh, right. This is our shader, and we're using 3D points now.
Yeah.
Great call. Still surprised it's not rendering anything. But
did we get rid of the face, all the calling stuff?
No, I turned that back on. Let's turn it back off.
Yeah.
Fuck yeah.
Yeah.
Whoa.
Yeah, it's weird.
Cool. Okay, so here it's totally called out. Why? Shouldn't something be in front of the camera? But we're looking at the back of it, so it's doing backface calling. Is that right?
Yeah, exactly.
Okay.
Some stuff is clipping away because it's behind the camera, and that's not going to draw because of the clip coordinates. But this is, we're looking at the back face. We're inside the cube right now.
We're inside the cube, and the walls are going like this. Okay. Yeah. I love it. That is freaking bonkers.
Yeah.
Okay, so then the next thing we need to do is our model view.
Yeah, position. And basically push the camera, push it away so that the camera, essentially either the camera's moving back or we're pushing the object away from the camera.
Yep. So this is another, and they do an identity.
They start with an identity and they mutate it.
Yeah.
Which makes sense. Let me.
I assume it takes a create, right?
Oh, just creates the identity.
Just create.
That's cool.
It's cool. Okay, and then we're going to translate. I love it. I'm sure we have a translate in GL matrix. Okay. Translate, and we're going to write into model view. And this is going to be a vec3 dot from values. So we're going to translate x nothing, y nothing, z like -4.
Yeah, and you actually have to pass in model view twice.
What?
The translate function has the output, but then you need also to no, you're looking at from translation right now.
Oh, sorry. Yeah, thank you. The mat4. Okay, great. That makes sense. Cool. All right, sick. And I think we set it.
Yeah. And so we should just see a square right now, like when this happens.
Correct, because we haven't rotated it at all.
Oh, we need to actually find the the uniform. Oh, you already added the uniform. Okay.
I already added that, yeah. We do what we do need to do, and this we can test this here. Oops. Fail. Oh, we need to set model view. What we do need to do is multiply this in though. Yeah. That's a square. Aspect ratio looks a little wrong to me.
Aspect, it does look a little wrong, but that's okay for now.
Yeah. Okay. Yeah. Let's give it a rotation first.
Okay.
This is gonna be mat for dot rotate of model view, and then I don't know.
Oh, this is
interesting.
45. It needs to be in radians, so it'd be the 45 times math.pi divided by 180. And then why don't we rotate it around the z-axis? It's 0, 0, 1. And we can rotate again around the x. Yeah.
I can do both, right?
Yeah.
Whoa! Look at us.
Yeah. There you go.
Why is it so blurry?
It is blurry, isn't it?
Yeah, I demand higher resolution.
That is interesting.
Is this low P? Let's go to high P. I don't think that's it. No, that'd be silly.
Yeah.
I was hopeful.
I don't know. I would have expected something a little bit higher in resolution, but it could be that we're not anti-aliasing currently.
Mm-hmm. The canvas width and height they need to be set on the actual HTML too. This is one of those things where we might need to actually calculate it.
Oh yeah, because this now looks now it looks correctly. It looks correct in terms of its.
That's because I set it to 100, 100. I'm just going to make this like 600 and height equals 5. Oh, you know what it is? It was rendering 300 by 150 pixels blown up.
I see because the style sheet.
Right. So we need to actually just grab the width and height in pixels.
Or we can set the width and height from the JavaScript as well.
Yep.
Because the 100% is scaling it, right? That's not actually setting it.
Correct. If I undo this, totally fine. Yeah. Right. Okay. So yeah, we'll take that out, and then I see what's going on. We can just do canvas.width equals document or window dot inner height and inner width.
Nice.
Didn't work at all.
Oh yeah, that's beautiful.
Yep. And then style equals.
You got that React.
That doesn't even work in HTML, doesn't it?
It does. You can do style. You can do a style property. Yeah.
Okay. Man, I've forgotten what's real and what's not in browsers these days. Hey, that looks like a really cool cube.
Dope. Yeah. And we can actually rotate a little bit on the y-axis as well, right? Let's do a little.
Oh, you want some more rotation? Yeah, we got more rotation.
0.5. Yeah. Oh yeah. See a little bit more. I want to see a little bit of the bottom there. Yeah, that's great. Gosh.
So if I turn off culling, it just renders. It's just rendering like the weirdest. Is this just the order that it sees the points and it's like?
Yeah, it's kind of.
Sorry, you drew it that way.
Yep, exactly. Although I do think that in this case, the face culling and the depth test are redundant to each other.
Okay.
As long as the, this is dope.
This is really, really cool. Okay. I sure feel like I understand some of this more now.
Yeah, it's kind of coming into focus a little bit, right? We didn't do textures. We didn't do lighting. That's all fine. Honestly, I
Yep.
think those concepts are in a vacuum relatively easy to understand.
Yeah,
Everything
that really just
else,
feels like making the fragment shader do some fragment shading.
exactly. Yeah, and then everything else is kind of just like on the CPU side. How do you organize your lights, your model geometry, your shaders, so that things happen quickly enough? Like how do you nest them? What's your hierarchy? What's your scene graph?
Oh yeah, that is this going to be harder than multiplayer, dude?
No, are you rotating? Oh yeah, nice.
Yeah, I was just going to do this.
Do we need? Maybe we should do a on an anim frame thing. So do it in an anim frame callback because I think while one might be a little. It's not going
Oh
to
yeah,
update
I
it.
think
Yeah.
I just crashed the browser.
Yeah.
Oops. Oh, fuck. Fucking should have known.
Let's call that function. Let's make that function just like call it draw or something like that. Oh, you can do. Yeah, you could just do this. This is totally fine.
Yo, I am so lazy. I'm sorry.
But the problem is we need to call request animation frame again, right? We need to call it like multiple times.
Oh, great point. Okay. Draw and then draw. All right, the laziness did not pay off. I gotta force quit Chrome. Fuck.
The whole thing?
Yeah,
Not just the tab? That's crazy.
I killed it.
Oh man.
That's okay.
What?
That looks awesome.
Yeah, nicely done. The fact that
Yeah,
it's
baby.
kind of rotating around 3 different. I wonder if we can actually see gimbal lock. Gimbal lock is not a concept that I understand particularly well, but it's basically that like. Well, we probably wouldn't see it in this case, but like, the idea is that if you try to compose rotations around the x, y, and z axes, which is known as Euler angles, you'll see weird discontinuities and pops when you do this kind of thing.
Oh, interesting.
Yeah.
It's looking good to me.
It looks good right now. Yeah, for sure it does.
All right, without call face.
That's freaky. This is like one of those like weird optical illusion things that we're seeing here.
Truly bizarre.
Yeah. We're looking at it in 4-dimensional space.
Oh wow, we are. Yeah. Okay. Back to the pretty cube. Great.
So yeah. So
I just want to see what our original colors looked like and if we were totally crazy or not.
Yeah.
Oh, actually, not as bad as I thought. It looks like we lit it.
It does a little bit, yeah.
Yeah. Okay.
It looks good.
It actually looks fine. Yeah. Clever us. All right. Well, I think we're ready to start doing some HD ultra graphics here.
Yeah, absolutely. I'm excited. I can show you how I did my wireframe rendering for if we're still interested in wireframe. We don't have to, of course.
Oh, cool. Yeah.
I think we can experiment with that as well.
Oh, I can imagine too that sounds like a fragment shader problem to me. Is that correct?
Actually, it's the way I did it is not. There are lots of different ways to do wireframe. I chose the way I did it because I like a lot of its properties, but it also does require pre-processing your geometry a little bit. Which
interesting. Okay. Cool. Well then, yeah, let's take a look at that next time.
Cool. Alrighty. I think it's time for Advent of Code.
Oh yeah, let's see what today's problem is.
Yeah.
Okay, a lot of Christmas themes. I see a regex.
Yep. If you're looking for a regex example, oh, you probably figured it out from last time.
Yeah, I used a regex for 2 ago. Yeah. All 8 fields are present. This is like a little more complex than a regex too, probably. I don't think they're ordered.
Okay. Oh, so we actually have to like legit parse it then.
Yeah. Or you could write 8 regexes and just fail if you don't match on any of them, but that seems a little brute forcey.
Oh, yeah.
Neat. I like this thing a lot. It's fun.
It's really fun, right?
Yeah.
Cool. All right, let's get to it.
Sweet.
All right.
Good night, Twitch.
Good night, Twitch.